Hello everyone, this is Dr. Young, and in this video we're going to talk about the last of the quantum numbers, the spin quantum number m sub s. And we'll talk about spin up, spin down, and kind of where the idea came from. So we're on the last one here, right? So we've talked about all these things beforehand and all three of these quantum numbers beforehand, n, l, and m sub l. Now we're on m sub s. Here's our big diagram, right, of all the quantum numbers, what they sort of mean, the acceptable values. We're down here now at the spin number, right, the spin quantum number, which refers to the spin of an electron. I put it in quotes, and I'll talk about that a little bit more in a second, but it's not really probably that the electrons are spinning, but that's how the term originally was used. And what we're going to see is that you can have two allowable values, 1/2 and -1/2, so things can be either spin up or spin down. So you can have arrows pointing up or arrows pointing down when we draw electrons in orbital diagrams here in a second, and I'll do an example of that in a little bit also. So the spin quantum number, sometimes it's called the magnetic spin quantum number, either one you'll see out there. And what was noticed was that two electrons in the same orbital did not seem to have exactly the same interactions in a magnetic field. And people could use spectroscopy to see that there are fine lines, fine differences between energy levels that they couldn't quite see before. And they're wondering, well, why? Why, when these electrons should have the same energy, why would there be a gap like this that means that they don't have the same energy? And so two young physicists thought that maybe these electrons were spinning. And we don't have to go to the physics of it, but if you have a object with a charge, like an electron, right? Electrons are negative. If you have an object with a charge and it's spinning, then it should be generating a field. And they thought, well, maybe this little magnetic field is what's causing the differences in what we're seeing in the spectroscopy. And so they call it the spin, and they published this paper about the spin of electrons. Now, later, people realized that it's probably not physically possible for electrons to be physically spinning, but the term stuck, and so we call it the spin of an electron, even though things aren't really spinning. And so you'll see these diagrams like this, where this red thing is supposed to be an electron. And the idea is that if it's spinning, in this case clockwise, if you're looking, or sorry, counterclockwise, if you're looking down on it, if you're spinning, it's going to be generating a field in a certain direction. If it spins the opposite direction, it's going to be generating a field in the opposite direction. And so we call that plus 1/2 and minus 1/2. That's a spin of plus 1/2 and a spin of minus 1/2. And those are the only allowable values for this m sub s. It's not like it relies on the m, the l, or the m sub l. It's either plus 1/2 or minus 1/2. And that was called either spin up or spin down. All right, so plus 1/2 was spin up. Minus 1/2 was spin down. And like I mentioned to you before, we drew this as either a spin up was an arrow kind of pointing up. It's a half arrow. That's a symbol for an electron. Spin down was drawn like that, where it's a half arrow pointing down. That was spin down. And so that's how we draw electrons once we put them into these atomic energy diagrams, which I'm going to show you here in just a second. So what that allows for us now is that we're able to put two electrons in each orbital. So now when I start to draw things like an s, right, say I have an s orbital, let's say this is a 2s orbital, and let's say this is a 2p orbital, and let's say this is like a 3d orbital. I'm not doing these in any particular order, I'm just trying to show examples. What we're saying is we can get, right, so this is one orbital. Let me get this language down for you, right? So in the 2p subshell, there are 3 orbitals, right? The -1, the 0, and the 1. And what we're saying is that in each orbital, we can put 2 electrons. So I can have 1 up and 1 down, 1 up, 1 down, 1 up, 1 down. I can have 2 electrons in each orbital. For this now is a total of 6 electrons. There's 6 electrons in the 2p subshell here. And I can do the same thing with all these other orbitals too. So 2s, it has 1 orbital, it can fit 2 electrons. So 2 electrons can go in the 2s. 3d, since it has 1, 2, 3, 4, 5 orbitals, it can hold 10 electrons, because again, every orbital can hold 2 electrons. So we would go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so we can get 10 electrons in the 3ds. And this is the last piece of information we need in order to make atomic orbital diagrams and to do electron configurations to describe the electronic structure of an atom. So for example, I'm going to do one example with nitrogen here, just so you can see me do this, but in the next video, we'll talk about this in a little bit more rigorous detail. So we've got nitrogen, which is right here, right? So boron, carbon, nitrogen. Here's nitrogen. And for atomic orbital diagrams, what you're basically do is you're going to show all the electrons and all the orbitals for a given element. And so if I look at nitrogen, for example, I know that nitrogen has, since it has an atomic number of 7, it has 7 electrons. Right? We're talking about just a neutral nitrogen atom. It has 7 electrons. So what I'm going to do is I'm going to draw the orbitals that it has. So here's my energy going up. I'm going to fill it like I normally do. You guys have seen me do this before, but always you start with the 1s. Always next is the 2s. Always next is the 2p. And that's all I really need for nitrogen because that's all I go through until I get there, right? So I go through the 1s's, I go through the 2s's, and now I'm in the 2p's. And what I do is I put these electrons in. So if I'm going to draw this atomic orbital diagram, I need to draw these 7 electrons. I go 1, 2, 3, 4, 5, 6, 7. And that's what the atomic orbital diagram for nitrogen looks like. What I wanted to point out, right, is when I draw these electrons in, I draw them as either spin up or spin down, and that they're different. And so what I'm going to do in the next video is talk about how on earth I came up with all of this stuff, why I started down here, why these are opposite here, but they're not opposite here, why didn't I pair them up here, right? We're going to talk about all of those rules about drawing atomic orbital diagrams in the next video. The main thing I want you to get out of this one is that the spin quantum number, or the magnetic spin quantum number, is just either plus 1/2 or minus 1/2 for any given electron. So for example, if I was to look at this electron right here, if I was to look at this electron right here, this electron would have a principal number of 2 because it's a 2s. It would have the angular momentum of 0 because it's an s orbital. It would have a m sub l of 0 also because s's only have zeros for their m sub l's. And lastly, for its spin number, that spin up one would be plus 1/2. And if I look at the other electron in that orbital, it would be 2 also, 0 also, 0 also, but now it would be minus 1/2. So it has a opposite spin. So they look really similar in terms of all of these quantum numbers. And right, I gave this in order of m, l, m sub l, and m sub s, right? That was the 4 quantum numbers for those 2 sets of electrons. What I just want you to get from the m sub s is that it's plus 1/2, minus 1/2, spin up, spin down, and that's really it. That's really it. So watch out for the next video where we're going to start talking about electron configurations and atomic orbital diagrams. So I'll tell you all about Hund's rule, Pauli exclusion principle, all of those sorts of things. So study up. Let me know if you have questions. Keep it out for the next video.